example 4 and 2.9. Use a calculator. Okay, all right. Well, this is easy enough. Here we go. Include at least 4 places after the decimal point. So what did you get for log 9? 0.9542. And then log 6125. 3.7871. Ooh, log base 2 of 10. Now, you're not just going to press your log button, because what did we talk about yesterday? The base on your log button is 10, and this is a base 2. So, depending on your calculator, go to your math menu, your math button, okay, and scroll on down, and some of you will have a thing, an option called log base, I think. It's either log base or base log. I don't have it, so I don't remember. Okay? And when you press that button, it allows you, it gives you a couple of boxes, and you just fill it in. Right? That's it. If you have an old calculator like mine, you don't have that option. It's just as easy. It's log 10 divided by log 2. So it's the log of the top number divided by the log of the bottom number. So, doesn't matter, however you did it with your particular calculator, you should have gotten 3.3219, right? And then same thing with log base 7 of 135. 2.5208. All right, everybody okay with that? All right, if we have time someday, I'll show you why this is true, and I'll also explain a little bit more about how logarithms work, like how they were developed, why they were developed, but right now let's just get through our material. Okay, so now, read that stuff right there, read that, what is that type there? And see if that makes sense to you. Would you agree that the exponential graph, the one on the left, is very hard to interpret at the beginning of the graph? The first half of the graph is almost impossible to interpret, and that's because exponential functions grow so fast that in order to get the last points into the grid, you have to really squish down the first points. So if we graph it logarithmically instead, now notice that the scale on your logarithmic curve, notice that this is 10 to the first, 10 to the second, 10 to the third. So your y's are powers of 10. Now, what does that mean in terms of, like if you were actually doing it on a graph? Well, let's turn the page and see. Example 5, population data, blah, 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 blah. Plot these additional data points on the graph above. Okay, so see if you can plot 1840, 1860, and 1880. Well, according to the picture, it's going to graph it at 220, 240, and 260. Those are the blanks that you have there. It says over here on this page, I think, yeah, it said 6 cents. Year 0 is 1620. So it's 220, 240, and 260. So So on your y-axis, 10 to the 7th is what number? 10 million, right? And so what would the next mark, if you were going to extend your vertical axis, the next one would be 10 to the 8th, which is 100 million. So you are plotting 17 million, 31 million, and 50 million, which are all less than 100 million. So they're all going to be under 10 to the 8th, in between 10 to the 7th and 10 to the 8th, okay? One common type of graph is seen below. So on your AP exam, if there is a logarithmically scaled graph to do, you'll have this kind of a graph paper. So I'm interested in you paying attention. First of all, these lines are not evenly spaced. You see that? So it's different than what you're used to. What would be the labels on all of these horizontal markings? They're not evenly spaced, even though I do it that way. They're not evenly spaced. What would be the labels on those? The bottom one, the x-axis, is 1. What's the line right above it going to be? 2? And then 3, 4, 5, 6, 7, 8, 9, 10? Now, what about after 10? You're going from 10 to 100. So it's 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. And then you're going from 100 to 1,000. So now they're 200, 300, 400. See how this works? That's how it works. So with that knowledge, plot those 5 points. Go ahead and plot those 5 points. 1, comma 20. Now remember, where is 20? Right after 10. Because you're counting by tens. Between 10 and 100, you're counting by tens. Between 100 and 1,000, you're counting by hundreds. Neighbor's paper. Find somebody to compare with, see if you match. So, I'll refer to make sure you match. If you have any kind of disagreement, let's talk about it, see if you can sort it out. Unlike any graphing you've ever done, that vertical axis is not consistent. So between 0 and 10, you're counting by ones. So each line is like up 1. But between 10 and 100, you're counting by tens. And then between 100 and 1,000, you're counting by hundreds. Okay, you got it? Okay, before we move on to the next page, we're going to need a piece of information, and I can't remember if we talked about it yet or not, so I want to throw it out there to you. This is an exponential expression. Anybody know what x equals? In the right ballpark. All right, this is an exponential expression. Let's rewrite it as a logarithmic expression. So remember how yesterday we had a to the x equals y? And that one became what? What logarithmic expression did this become? Log base a of y equals x, right? Now this is bigger and uglier, but let's do the same thing. So it's going to be log base a of x equals log base a of b, right? Well, wait a second. Log base a of x equals log base a of b. What does that mean? X equals b. So this is a property of logarithms that we're going to need here in a little bit in these exercises. So if you had the log base, if you had 7 to the log base 7 of 6, the answer would be 6. Okay, that's a property. We just kind of proved it, but from now on we're just going to say, okay, that's 6. Similarly, if you have 8 to the log base x of 7 equal to 7, then you know x has to be 8. These have to match, or these to match. Okay? All right. Let's go on to the next page then. Okay, here we go. We can graph logarithmic functions. We know this. What does the graph, a logarithmic graph, look like? It has an asymptote. I've got labels. It has an asymptote where x is 0. It has an intercept at 1 because the log of 1 is 0 because a to the y is 1. So y has to be 0. And it looks like, yeah, do you remember that? That's your logarithmic curve, which is the inverse of your exponential curve. We talked about that yesterday. See that relationship? The logarithm has an asymptote at x equals 0. The exponential has an asymptote at y equals 0. That makes sense. They're inverses. Ordered pairs got switched. All right, so that's your logarithmic curve. All right. Recall that for exponential functions over equal width input value intervals, the output values change multiplicatively or proportionally, right? We know that. So if we look at this example, x's are going up by 2. We call that they're changing additively. We keep adding 2. But for the y's, we keep multiplying by 2. That makes it exponential. Now what's going to happen when we do the inverse? When we do the inverse, the x's are going to grow multiplicatively, and the y's are going to grow additively. Okay, so start compiling all this. If I give you a table of values, you know how to tell if it's linear, you know how to tell if it's quadratic, you know how to tell if it's exponential. Now you know how to tell if it's logarithmic. A logarithmic set of data, the inputs, or the x's, are going to grow multiplicatively. Times 2, times 2, times 2, times a half, times a half, times a half. They're going to grow proportionally. While the y's, or the outputs, are going to grow additively. Got it? All right, let's try example 1. Go ahead and figure it out. Look at all of them. Figure out what kind of table of values you have there in example 1. All right? Who can give me an answer and explain it to number A, letter A? What do you think's going on in A? Exponential. Why, Caitlin?
Because the x is going up by 1, and then the y is going up by a half.
Okay, so your inputs are growing additively, you're adding 1, and your outputs are growing multiplicative, or shrinking multiplicatively, you're multiplying by a half. Good. What about B? Who can explain that one? So your inputs are growing multiplicatively times 3, and your outputs are growing additively plus 10, logarithmic. All right, how about C?
Either.
Because?
Well, the left side is increasing multiplicatively, but on the right side, from 4 to 8, it's not like a consistent additive.
So we are actually, aren't both sides growing multiplicatively? So the inputs are going times 10 and the outputs are going times 2? Right? Charlie?
What would that make?
I don't know. How about D? What'd you get for D? Logarithmic. Inputs are growing multiplicatively times 2. Outputs are shrinking additively by -3. Good, easy enough. All right, next page. We have discussed how logarithms and exponentials are inverses. There's their relationship. It's very, very clear and easy to produce. Now you're going to prove it. And some of you are a little lax in your proving. So let's run through this and make sure everybody is being adequate. And the reason I want you to be adequate is this could be a free response question or part of a free response question where you need to prove that two things are inverses. That may not be these kinds of things, but you need to prove that two things are inverses. So that's what this direction says. Show that they're inverses, okay? And we know we do that by showing that f of g of x is x and g of f of x is x. That's our proof. That's how we do it. So, let's go through it. Here we go. F of g of x will be 3 to the log base 3 of x. Would you agree with that? F of g of x. Is that okay? And we just talked about it. What does that equal? X. And then g of f of x will be the log base 3 of 3 to the x. And that one we already know. What is the log base 3 of 3 to the x? Just x. In case you forgot, that would be the log base 3 of 3 to the x would be x. Exponents come out in front. X, log base 3 of 3, and log base 3 of 3 is 1. Okay. Since f of g of x equals g of f of x equals x, f of x and g of x are inverses. You need to make sure, and this is true of anything you're ever proving anywhere in math class, you assume that your reader knows nothing. And so you have to be really clear. You can't just do this work and say they're inverses. Because that assumes I know this. Don't assume I know anything. Write down what does that mean? Well, it means they're inverses because of that. All right, good job. Example 3. A portion is shown on the graph below. Sketch a picture on the same coordinate grid. So go ahead and do that. We're sketching a logarithm, so it's going to be the inverse of the exponential. So some points you'll have would be what? 0, 1, you can plot at 1, 0. How about 1, 2? You can plot at 2, 1. Let's see, 2, 4 can be plotted at 4, 2. How about negative 1, 1/2? You could plot at 1/2, negative 1. Are you seeing your logarithmic curve come out of that? Sketching it in? Perfect. All right, and then example 4, Mr. Passwater's trying to get tricky, but I don't think he can get tricky with you. I think you know what's going on here. We have an exponential that contains the points 2, 3, and 627. And you're going to find the average rate of change for the corresponding logarithm. Well, if these are the ordered pairs for the exponential, what are the ordered pairs for the logarithm? 3, 2, and 27, 6. So your average rate of change is, I'll call this g of x. Our average rate of change will be g of 27 minus g of 3 over 27 minus 3. So 6 minus 2. Did you get 1/6? Check my arithmetic. What you got? Perfect. All right. I don't want to do the whole mystery function, but I want to do part of this. The next page, the mystery function. Right now, with your partner, can you fill in, can you figure out what's going on there and fill in those missing numbers? And then, when you're figured out, do number 2, which says write an equation for what you've discovered. What is the rule or the equation for that mystery function? we coming? Do you think we have a plan, have an idea what's going on? Yeah? What did you put under the 2 in the chart? What y value went with 2? 1. What y value went with 1? 0. 1/8 was -3. 64 was 6. 0 was no, can do. Can't do that one. I don't think. 1/4 was -2. -1 was. Can't do that one either. How about 3? 1.585. You can do that one, but you need a calculator for that one. Who discovered a rule? What's going on there? How did you get those numbers, Charlie?
So when x divides by 2, the y values go down 1.
Did you come up with an equation for
Oh,
that?
an equation, my bad. No, I did not.
I said the same thing Violet did, but I said it differently. I said 2 to the y equals x. And then Violet said log base 2 of x equals y. These are exactly the same equation. I thought about it as an exponent. She thought about it as a logarithmic function. Now, why were we unable to find an answer for 0? If you use my equation, or either one of them, if x is 0, then mine would say 2 to a power equals 0. And Violet's would say the log base 2 of 0 equals what? And we know that the logarithmic function, any base, has an asymptote at 0. X cannot be 0. You cannot raise 2 to a power and get nothing. You can raise 2 to a power and get small, but you can't ever get nothing. Would you agree with that? Now, why were we not able to do -1? Can you raise 2 to a power and get a negative number? No. Can you take the logarithm of a negative number? No, it's not in the domain. No x's over here. Not possible. Good job. Good job. All right. Back to that page. You and your partner start filling it out as much as you can. Maybe you can do it all. Let's try not to use a calculator. I think you can do it without. I'm going to hand out some stuff while you're doing that. So did I get everybody else next set? Okay. Log base 2 of 32 is 5. Log base 5 of 5 is 1. Log base 36 of 6 is 1/2. You guys are awesome. Log of 100, or log of 1/100 is -2. And the natural log of e cubed is 3. Everybody okay with all that? Easy. All right, fill in the table. We're gonna do F first. 3 to the -1st would be 1/3. 3 to the 0th is 1. 3 to the 1st is 3. 3 to the 2nd is 9. 3 to the 3rd is 27. Right? Now, G is the inverse. So if 3 to the -1st was 1/3, then what's the log of 1/3? Base 3 of 1/3? -1. You're just flipping those ordered pairs. So under the 1/3 is going to be -1. Under the 1 is going to be 0. Under the 3 is going to be 1. Under the 9 is going to be 2. Now he got tricky. What's going to go with the 81? 4. Because 3 to the 4th is 81. Is everybody okay with that? All right. So F and G are inverses. I'm not gonna make you do this, but if you did find G of F of X and F of G of X, they would both equal X. It's like the one we just did a little bit ago. They would both equal X. See, as the inputs of F grow additively, the outputs grow multiplicatively because F is exponential. And then for G, as the inputs grow multiplicatively, the outputs grow additively. We all good? Okay. What we're gonna do now then is stop, because we finished 2:9 and we finished 2:10. So now you have 2 homework assignments to do. So I'm gonna give you 10 and 12 minutes, because who's the nicest person ever? And you that's right. You can go ahead and get started on that, and those will both be due on Monday, okay? Now, I know that we have Christmas on the Hill, but there is nothing stopping you from bringing them in at your convenience, either tomorrow or Monday.
Do they do anything on like the 4th during Christmas on the Hill?
I don't think so.
I don't think so either. I think it's okay.
So, the Christmas on the Hill doesn't end like before normal school ends? I'm trying to remember.
I think it ends like 2:30.
Yeah, so you can bring it after school.
Okay.
If that's easier, or you can bring it before school if that's easier. I have office hours on Monday, so if you have it done, you can bring it in. I mean, seriously, today's Thursday, you got quite a bit of time. I'm giving you time right now to get started.